So back to the generative adversarial network. So we discussed last time GANs, right? We started with GANs, and then we talked about this, that why we are going for GANs, right? So we finished with the explicit methods. In the explicit methods, we were really obsessed with the data distribution. We wanted to really know what is the chance of every single sample, right? But now we are not anymore obsessed with that. The thing that we would like to know is that how we can sample from that distribution. And if we can sample from that distribution without knowing the distribution itself, we are totally happy, right? So this was the idea of the generative model in general. So if I have this generative model, I can again think as in flow-based models, but now I can just take any restriction from this generative model, right? So I have some latent representation Z. This guy goes inside the model. As the output, I'm going to get one sample X hat. So X hat is essentially this transform. So Z go inside, the output of this transform is X hat, and this guy is distributed with some distribution, right? Because X is distributed with some distribution. Now, if my model is very generic here, very, say, deep neural network with so many layers which can represent or somehow estimate any function, and maybe I have a bunch of randomness inside it, a few random things generated and added inside this model, then the output could be quite general, right? It could have any distribution. And then the whole point is that I want to make this distribution to look like the data distribution, right? We talked about this, that if we want to do it, we cannot explicitly use maximum likelihood. What was the issue by using the maximum likelihood? We could not compute the output probability explicitly, right? So when you want to compute this one, you can use the variable exchange, but you end up with that weird, integral, right? So you're going to have lots of terms showing up. Your set inside the latent space, which is connected to your corresponding point inside the data space, is not very clear to you anymore. And because of that, you're going to have a hard time computing that probability. It's not feasible. So we do not exactly know what is the output of this model, the distribution of this model, right? We can put one random input into it. We get one random output. That we can do. But we cannot explicitly write down the distribution of the output as we could, for instance, in the flow-based models, right? So that was the issue that we had. And the solution we came up with was this intuitive solution that we use the kind of model we call a discriminator. So what is the discriminator? This guy is going to get this X hat, this particular sample that we have generated from our model. So we took one Gaussian noise, we gave it to the generator. This gave us X hat, and then we are giving X hat to the discriminator, and we are going to classify it. So we classify it as a fake if this is coming from the model, or we are taking, if this is the particular guy which is coming from the data set, so if we have the real sample, then we are going to classify or label it as real, right? And the discriminator here, what it does, it's going to get samples from the model. Also, it has samples from data set. And it's going to compare them, does some operation on them, to somehow understand these are not the same. And then it tries to give back some information to the generator. And generator, out of that information, it tries to update itself, right? Such that gradually, as we go on, this generator is able to generate some samples which look exactly like the data samples. And because of that, the discriminator is no more able to suppress or distinguish between the real and fake samples, right? This is the intuitive idea of how we can realize or train a generative adversarial network. This is what we call it adversarial setting. An adversarial network, I mean, of course, this is the best place for it is for data generation, but it has also its own application in other domains as well. So this idea of having something and then one discriminator which is trying to suppress or somehow gives play a kind of min-max game with the other side of the network. This is the idea of adversarial network. And one hint beside, don't confuse yourself with adversarial training. That is something totally different, okay? So in adversarial training, you assume that your data samples are contaminated with something. So that is another story. We are not doing adversarial training, okay? So it's just the name, adversarial network. We call that kind of configuration, discriminator, generator, adversarial network, okay? But here the adversary is not doing a bad thing to us. It's not harming us. It's trying to push us forward to just generate data-like samples, okay? So now, if you got the idea generally, then let's try to formulate how we can train such an architecture using basically, for the moment, the knowledge we have from deep learning. So let's put ourselves at the place of the discriminator. What does the discriminator do? It's going to have a bunch of samples coming from the model, right? Say you have 1,000 samples in your data set. You can also generate 1,000 samples from your model, right? Just sample 1,000 noise samples and then send them through the model. It's going to give you 1,000 samples from the model, right? That is very easy for you, right? Now, you can make one data set out of these guys, right? So you can make one data set of this form, and inside this data set, say I am now talking about general n, inside this guy, you're going to have 2 times n different data points, right? For every single data point that you had in your original data set, you can generate also one sample from the model, right? Now, we're going to label the model sample to be 0. It means this is fake image. And then we'll label the data sample to be 1, right? Clear? Now, this is a data set for a supervised learning, for a classification problem, right? And then for the discriminator, the only thing that it needs to do is to solve that classification problem, right? So it wants to classify the sample that is coming into it, whether it is a fake or real sample, right? So from that point of view, so this guy, as I told you, this is real data sample. So xj is essentially the one which you had in your original data set. You label it with 1. This other one is fake one, which you have generated with your model. And now your discriminator is going to just solve a classification problem. And for this classification problem, this has this particular data set, right? So I can now write it down in this form. I'm writing it down now. You see here, initially I put it x hat, but now I am dropping that hat and just write it down x and v, any x and v, and then I have 2n of them, right? N of them was coming from the original data set, n of them I generated with my model, right? Now this is a classical data set for a binary classification, right? And the labels in this binary classification are 1 when everything is coming from the data distribution, or this is a real sample, or it's fake when it's just coming as the output of the generator, right? Everybody's cool, right? So discriminator has this data set and wants to accomplish this binary classification task. How can we do it? How you can solve a binary classification? You're going to put a model, right? A neural network. You give x as the input, right? And then at the output, you're going to compute a sigmoid. That sigmoid is going to be the probability of 1, right? And then based on that, you're going to decide whether this is a fake or real image, right? So that is something very easy for all of us, given what we had before in machine learning courses, right? So we can simply do that. We can simply use one computational discriminator. By computational discriminator, I simply mean one binary classifier, right? It could be as simple as linear, like logistic regression, right? As simple as that one. Or it could be a very deep neural network, with the last layer being a sigmoid, right? So we're going to have this particular guy. This is one neural network. And this neural network, it's going to take input inside the data space, right? It's a d-dimensional input because the inputs that we are, or the samples that we are going to classify are exactly the data samples, right? So we have input to be the data sample, and the output is going to be something between 0 and 1. It is essentially the probability of label being 1, right? Clear? Great. Now, as I said, you can have a sigmoid output. This classifier is what we call a computational discriminator, and consider this one to has parameters phi, right? So these are the weights of its own neural network. Now, whatever it computes is going to be the probability of your particular label given x, right? And now, this guy is essentially a discriminative model, right? This is not a generative model, correct? Because I am computing the probability of a label given the input, correct? I am not yet computing anything about the probability of x. Eventually, we're not going to compute it at all, right? We just compute it implicitly, not explicitly. You're going to see that, right? So this is discriminative model. This is why we call it discriminator in this architecture, right? Because it's a discriminative model inside the architecture. Everybody's clear? It's the guy which is doing discrimination. It's not real. It's fake, right? It's just discriminating. It's just giving like harsh feedback to the generator, right? Cool. So now if I want to classify it, to train this guy, how can I do it? I can do it by cross-entropy, right? We had it in the deep learning course. We have it in the machine learning course. Any course you had before, you always do that when you want to do binary classification. With a sigmoid output, it's easy to simply just do it by cross-entropy. And the cross-entropy, how do we define it? This is the expression we had for binary cross-entropy. But let's just write it down in more simple form. So this is essentially the case. So if I put v here equal by 1, meaning that when the data is labeled as real. So what's going to happen? If I put v equal by 1, then the first term going to remain. What's going to happen to the second term? 0, right? So it's going to be minus log of the output, right? Minus log of the output of the discriminator here. Why? If my sample x is a real sample, right? Now, what's going to happen if I put v equal by 0? First term 0, the second term going to show up, right? So it's going to be minus log of 1 minus the output of the discriminator. This is the probability of the image being fake, right? The output, the sample being fake. So if the sample is fake, or the label is 0, then it's going to be essentially minus log of 1 minus the output, right? Everybody's clear? And one point that you should pay attention here, I know this is simple, but just that you don't get lost. This y, what is it exactly? This is the output of this model, right? So I can essentially write y equal by this d phi of x, right? D phi is the neural network, x goes in, as the output you're going to get y, right? So that is the value, exact value coming out of your discriminator. Everybody's cool? Okay. So now that we have this, let's try to just compute the empirical risk and minimize it to train this model, right? So how can I compute the empirical risk? Well, I need, for every single sample inside my data set, I'm going to compute the cross-entropy between the output of the model, which is y, and the true label v, right? Correct? Now, I have 2n different samples in general, right? So I'm going to compute all of them, add them up, divide by 1 over 2n, right? But one thing that you do know is that those 2n models, 2n samples, sorry, n of them are exactly labeled 1, n of them are exactly labeled 0, right? Correct? Everybody's cool? Yeah.
Would there be cases where you want to have more or less of each one, or is it always 50-50?
Yeah, this is a good question. Like, it turns out that best idea is to have 50-50, right? But this is a very valid question. It's not like immediately seen here, right? But in the original idea, they actually did not discuss it. Later on, some ideas came out which call it label smoothing, meaning that you don't really touch the number of samples, but you just change the idea how many samples you have. But eventually it turns out if you don't do it 50-50, then you are not going to benefit too much. Now a rough idea why this is going to happen is because if you have like more of one, less of the other, then the one which has less samples is going to have higher variance in the estimation, right? And then this is going to dominate the whole thing. So it doesn't make sense to really share things unequal, right? So this is the statistical idea, but this is totally valid question. And then people have tried studies to understand why exactly it should be 50-50.
No, that makes sense.
No,
Thank you.
no worries.
Hey, Professor, I just have a question, like, how do we get a fake data set in the first place? Are we just rely on the output of generator?
Yes, output of generator.
And without training the generator, we just use it, like, for example, if you want to have 50 data sample, we just run it 50 times?
Yes.
And does the quality of the
initial one is very bad, yes, of course. So initially you generate 50 samples of noise, and then you pass all of them through your generator. You're going to get 50 samples, which are totally nonsense, right? Now, you give it to your discriminator, it can easily say that these are fake, right? So there is no error in the classification. Then we are going to compute some sort of gradient, we push it backward. Then that model that generator is going to get updated. Again, you generate new 50 noise samples and pass it through the updated model. You get the new batch, and then again you train. Okay? So you keep on doing it. Each time the W gets updated, those samples are getting more and more close to the real samples, right? And at some point, discriminator is unable to say that they are fake. No? No worries. Questions? No question. Okay. So as I told you, 50% label 0, 50% label 1, right? And those which are labeled 0 are essentially those coming out of the generator, right? Label 1 coming from the data set. So I can write it down in this form. So this output, I mean, first of all, let's just replace this D here, Y here, by the output of the discriminator. Sorry, I forgot this step. So Y is essentially D of the output of the discriminator, right? For the discriminator is going to take the X and give you Y, right? And now I can open it up in this form. The first N samples are essentially the guys which are these X's which are coming from the data set, right? Correct? So they are all labeled by 1 because they are real samples, right? And you have N other samples which are coming from your model. So you can write it down as the samples coming out of your model compared with the true label, which is 0, label fake, right? Now, how can I write down those samples which are coming out of my generator? How can I write that down? How I generate one sample? We already talked about this. So I'm going to sample one noise, one latent, right? And pass it through the generator, right? So inside that D file, inside the brackets, what can I write? I can write G of Z, right? G of one sample noise, right? So I can write it down G of Zj. And Zj is one sample noise that I have taken from my latent distribution, Gaussian distribution. For GANs, in practice, we always use Gaussian. Okay? Everybody's cool? So you agree on what I've written here, right? Okay, cool. Now, looking at this, now let me first replace this cross entropy with the exact expression. When the label is 1, what's going to be the cross entropy? We had it in the previous slide. Minus log of y, and y here is d, right? So this first term, instead of the whole green term, I can write down minus log of d, right? What about this one? Minus log 1 minus d. So I can write down minus log 1 minus d g z, right? Right? So I'm going to do that. So the first one, okay, I felt like, okay, this is when I do the tutorial before my lecture, so I do not have time to review the animation, right? So Yeah, I wanted to write this down. Right? Let me first write that down, because I explain and then I get back here. So this guy is minus log of d phi, right? And the other one, this cross entropy of anything and 0, is going to be minus log of 1 minus that thing, right? So I can write that one here down. Everybody's cool? And now, everybody's happy with this notation that I have used, because I have 1 over n summation of the data sample, so I can say this is approximation of the expectation over the data distribution, right? So it's going to be e hat of x distributed with p, because every single x I have here is distributed with distribution of the data, right? And then for the second term, I can again do the same thing, right? So I can say every single z here is sampled from the latent distribution q. So this 1 over n summation is essentially e hat of z distributed by q, right? Everybody's cool? So this is going to be the final expression or the final form of the empirical risk, right? And as you can see, this empirical risk depends on both guys. It depends on the discriminator model, phi, and it also depends on the generator model, right? Where does the discriminator show up? It shows up very early, right? It shows up here right away, right? Because this is the classifier, and we are just using the output of the classifier. So the risk is going to depend on that guy. Where does the generator show up? When we get here, right? When we want to fill out this expression, this sample, the model sample, that is coming from the generator, right? And that also depends on the generator parameters, right? So this means that when the generator parameter changes, this empirical risk is also going to change, right? So your empirical risk depends on both generator and discriminator, right? Everybody's cool? Questions on that? No question? Okay. Now, one last thing. I'm going to take this minus out, okay? And if I take the minus out, this is going to be the first term plus the second term. The first term, if you look at them, they're pretty much the same. One of them is log of d itself. The other one is log of 1 minus d, right? The two different probabilities, right? Okay. Now, as I said, empirical risk depends on both discriminator and generator, and this is the point where we can compute some information to give back to the generator, right? Because if we compute the gradient of this guy, we can also compute the gradient with respect to generator. And if we understand how exactly we need to use that gradient to improve the generator, we can pass it backward, right? Okay. Now, at the end of the day, this is going to be the problem. We want to do the empirical risk minimization, meaning that we want to just minimize this guy. Instead of minimizing this one, we can just maximize the minus one, right? So meaning that I'm going to drop this minus here, and I maximize anything inside it, right? This is when I want to do what? When I want to train my discriminator, right? So don't get lost here. We did the whole computation as the risk, empirical risk, for training the discriminator, right? This is just the average cross entropy. If we want to just train the discriminator, we are going to minimize it. But if we want to minimize it, with respect to what parameter are we going to minimize it? Phi, exactly. So phi is the guy which is showing the discriminator. If we want to train our discriminator, we are going to minimize it with respect to phi, right? We still don't know how exactly we can use w, right? The only thing that we know is that it depends also on w, right? Everybody's cool? So one side question. If I drop this minus, this expression inside the bracket without minus, what is that guy to you? Likelihood, great. So that is likelihood, right? That is log likelihood of the discriminative model, right? Okay, great. So now, at this point, the discriminator and generator start, since the loss depends on both of them, they start to play a kind of game, a min-max game. So what is the idea here? What is the best thing for the discriminator? The best thing for the discriminator is to minimize this guy, right? Because it wants to classify as accurate as possible, right? So it's going to go ahead and minimize this one. So the discriminator wants to classify correctly fake from real, right? So it wants to have it minimized over phi, right? So it's going to tune phi in a way that this expression is minimized, correct? So in other words, say the generator is fixed, it wants to do its best. How can it do it? It's going to just train by this approach. And if it can really find the best phi which minimizes this empirical risk, then that is the best classification that it can do, right? This is equivalent to maximum likelihood, right? Okay, so essentially the thing that it wants to do, it wants to minimize it with respect to phi. This is equivalent that I just maximize the whole likelihood, right? So I drop this minus here, and then I just do the maximization, correct? So this expression here, which is the minus that one, as I told you, this is the likelihood. I'm going to show it from now on by L, okay? So I'm going to show this guy by L. This is essentially minus the empirical risk. And the thing that I want to do is to just maximize it, right, over phi. This is what I can do best as a discriminator, right? This is the best classification I can do. Everybody's cool? Questions? No question? Great. Now, so if it does this, and right now I am just fixing the generator, right? So it is now, for that particular generator that I have, it is able to classify as accurate as possible, right? So it's not necessarily doing perfect accuracy, because it might be that the generator is really sampling from data distribution, then it can do nothing, right? But if it is just sampling from any other distribution, which is not the data distribution, it is doing its best, right? Because it's just maximizing the likelihood, right? Everybody's clear? Moral of the story, if I fix the generator W here, then by maximizing this likelihood term over phi, the thing that I'm getting is the best sort of likelihood I would get for that particular generator, right? Now that discriminator has done its job, then let's look at the generator. What does generator want? To make accurate samples. So how does it want to play with the discriminator? What is the ideal case for the generator in that sense? If discriminator is trying its best to classify what's generated by the generator, what is the best thing for the generator could happen?
Always be classified as 1.
Yeah, always classifies it as 1, even though the true class is 0, right? So it means that it always push up the empirical risk, right? Or in other words, it always pushes down the likelihood, right? Everybody's clear? So what the generator wants the discriminator to do, this is the best that discriminator could do. This is the maximum likelihood that discriminator could compute, right? And then the generator wants to make this likelihood as small as possible, right? Because it wants the discriminator to always do mistake, correct? If the likelihood just comes down, even though that the discriminator does its best, it simply means that the discriminator is unable to detect the fake images, right? Any fake image goes to it, it can always say it's a correct image, right? If a real image. Everybody's clear? So from the generator point of view, the whole idea is that it wants to just confuse discriminator as much as possible so that the discriminator cannot distinguish between the fake and real image. It means that whatever goes inside is supposed to always get classified as real, right? Even if it is fake. And if it wants to do that, the only power that the generator has is to play with its own parameters, right? And then you're going to play with them such that it's going to make that likelihood, which the discriminator tried its best to maximize, it tries to make it minimum, right? So in other words, it's going to just look at this optimal likelihood computed by the discriminator for the given W and tries to play around with this W such that this is minimized, right? Everybody's clear? Questions on that? No question? So, discriminator tries its best to just do the classification. Once it does it, then generator, it tries its best to just ruin whatever discriminator has done, right? Yeah? And this is the min-max game, right? So this guy is trying to push hard to accurate classification. The other one is trying to push hard to confuse it, right? This is the idea of min-max game. And from the statistical point of view, if you want to talk with respect to the likelihood, as I told you, discriminator tries to maximize its likelihood, but then generator tries to minimize this maximal likelihood, right? So it wants to play with its W such that even if discriminator tries its best to maximize it, it's not going to get a really high likelihood, right? And this means that the discriminator is going to always remain confused. It can never say this is a fake image, right? And this is basically what we want to happen, right? Yes?
I guess this is kind of a vague question, but how is it that these guys aren't going to like cancel each other out? Like the generator is going to get better at generating samples, and the discriminator is going to get better at discriminating samples.
Yeah, but once the generator gets very good, you should pay attention. Like in this story here, there is always a lower bound on the error that you can achieve, right? So it doesn't mean that if you are really sampling from data distribution, if the generator is really sampling from data distribution, there exists no classifier on Earth which can classify it from the true data distribution, right? If I am giving you cat image, no classifier on Earth could say that this is a dog, right?
Otherwise it would be wrong.
It would be wrong, exactly, right? So there's always a base lower bound on the error that the discriminator can achieve, right? And the discriminator can never go below that, right? Yeah, so if the distribution of the generator is very close to the distribution of the data, the true data distribution, then whatever the best discriminator you design, it doesn't matter. I mean, it's not about neural network or something. If you just think about any possible function on Earth, not on Earth, in the universe, essentially, that you want to put there to do the classification for you. That function, whatever, even the best one, is going to do mistake, right? Because the distribution which is very close to the data distribution, it means that once upon a time it's going to really generate some cat, right? And that cat is really a cat. So your discriminator cannot say it's not a cat, right? Yeah. Yeah, and then you are just pushing that error up and up and up. Or in another term, you're pushing down the likelihood, right? Because that error is essentially minus likelihood, right? Like proportional to minus likelihood, right?
Yeah, I think that makes sense.
Yeah.
We want one of these guys to get better, not like...
Exactly.
Okay.
Yeah, we just want to make it like generator as good as possible, so that whatever discriminator does, it cannot distinguish between what it has generated and what is the true data. And this essentially means that what it has generated is true data, right?
That makes sense.
Okay? No worries. So, questions? Everybody's clear on that? Yeah.
Does it make sense to make it a zero-sum min-max thing for the, like just to regularize the likelihood?
Just zero sum. But why we need zero sum constraint? I'm not sure. What do you mean exactly by zero sum?
If generator does like too good, then discriminator is like does like basically random guessing.
Oh yes, you can do that, but I don't think that is going to benefit you computationally anything. But theoretically, probably if you think about that, this is going to just somehow bound again the kind of error that you can achieve, right? But we are going in the next section I'm going to show that once this problem is solved, like if you really can solve this min-max problem, then the G model that is coming out of it is going to exactly sample from the data distribution. And because of that, even if you make it like zero sum, it doesn't matter. At the end of the day, the error is going to always be absolutely 1. In your case, it's going to be always half, right? Like randomly you guess, right? But it doesn't change the fact that you're really sampling from the data distribution. If I got your question properly. Yeah. Questions? No question? Okay, so then if you got no question, then this is essentially going to be the like official form of the generative adversarial network, or essentially this is the vanilla one, which we're going to talk about. Today we're only going to talk about the vanilla. Yeah. So if you have a generative adversarial network, it essentially consists of one generator. So the generator is a neural network. It's going to take latent, it's going to reform it into data. And then it's going to have a discriminator. This discriminator is simply a classifier. It's going to get a data sample, and then it's going to classify it as 0 or 1, right? And they are going to just play this min-max game, right? So the whole training is done by this min-max game, where we are going to maximize everything with respect to the discriminator parameters and minimize everything with respect to the generator parameters, right? And then this likelihood term, which we are the objective term, which we are going to put inside this min-max game, is this guy, which is essentially the likelihood computed at the discriminator side, right? And now, if we want to get back to the diagram we had, again, we have this particular latent. This is going through the generator. It's going to give us one sample. Then this guy, during the training, it had access to the data samples, right? So it got trained to very accurately sample the data, right? Classify whatever it gets. And now, what it's going to try to do, it's going to look at this sample generated by the generator, and it's going to classify it to see whether this is a real or fake image, right? And if the generator does a good job, this is going to always be classified as the real image, right? Now, when we are doing the training, what are we passing backward then? The gradient of this loss with respect to? W, exactly. So this is the whole thing. So we need the discriminator here to get this y. Why do we need this y? Because when we want to do the generation at the end of this story, say we have trained everything here, right? I don't need the discriminator anymore, right? I just sample noise, get the image, right? I don't really need to check it anymore by a discriminator, correct? So the discriminator is showing up here because I want to do the training, right? And then why do I need the discriminator? I need to get the output of the classification, right? And then out of this output, I am able to compute the loss, correct? And now that I have this loss, I can solve this problem. I mean, I am doing the maximization over phi. This means that I have a gradient with respect to phi, which is going to update my discriminator. Okay, that's fine, right? But also, I am able to compute the gradient with respect to w, which is going to help me solve the minimization with respect to the generator, right? And this is what I'm going to pass backward, right? So the kind of feedback this discriminator is going to give this guy is essentially the gradient of that likelihood with respect to the model, right? So it's going to say that the gradient of the likelihood term I computed with respect to your parameters is this one, right? And then the generator is going to update its weights using that gradient, right? And keeping on doing this is going to be to converge into the one which is supposedly just mimicking the data distribution. Questions? Everybody's cool? So you got the idea how GAN works, right? And this discriminator, as I told you, this is something that we need to add in order to do the training, right? We don't really need it for sampling or generation. No? Okay, cool. Now, if you got the idea, then this is going to be the training loop of this vanilla GAN. So we have this particular, say we have one particular data set D, then we fix the generator model. We also fix the discriminator model exactly as we discussed in the previous slides. So the dimensions are totally up to you. So essentially, you can generate, I mean, here it's not anymore flow-based model, right? So your latent space, your latent z, could be coming from any dimension, right? And that's totally your choice. You can essentially start with the small dimensions and then gradually go up to get into high quality, right? So we're going to have the generator and discriminator. We're going to initiate them, and then we get into the training loop. Inside the training loop, first of all, we are going to sample a batch of data from the data set, right? This is what we have for training. We are also going to sample a batch of noise samples, right? The latent samples. So I do know the latent distribution. It's a Gaussian distribution. I'm going to sample n different Gaussian samples, right? And then I pass all of them through my model. My model G is not yet trained. It's in the process of training, right? So at the beginning, it's going to generate very nonsense output, right? Which can easily be classified by the discriminator as fake samples, right? So this is going to do that. And now, once I have my batch, which includes both fake and real samples, then I'm going inside the loop. Now, here is one point, and one thing that you should pay attention. When I am computing this L, as I told you, this depends on both discriminator model and also x hat. X hat here is coming out of the generator, right? Now, I compute that loss, and I compute the gradient with respect to discriminator, right? Now, when I do that, after this, I am going to update my discriminator, right? Now, I do multiple iterations for discriminator to get updated. Once it got multiple iterations updated, okay? So you do a couple of iterations with fixed generator, okay? Once it got a bit converging, then you update your generator once, right? And then again, you're going to keep doing it. And the reason is because the minimization is out of the loop, maximization is inside the loop, right? So you are minimizing the maximize function, right? So if you want to do with the same order, with the same number of iterations, like for every iterations on phi, you do the same iteration on w, then you are going to have trouble converging, okay? So it's a kind of crucial thing. And this number is usually 5, 6, 10, something like this, okay? It's not big, but it's important to have different order. So you are going to update this phi, and you keep on doing it for some number of iterations, say z number of iterations, right? Once you have done this, now that you are over, so when you are at the very last iteration of the inner loop, then you compute the gradient with respect to generator, and you update your generator once, right? And then again, you keep on doing this. So for the next time, for the next inner loop, you're going to do, say, 10 times update of the discriminator, and then you again update the generator once, right? You keep on going like that. Everybody's clear? Okay. So once you have this, iterations run enough, then eventually you're going to end up with trained generator. For sampling, you only need the generator, right? You can have the discriminator to evaluate your model, for instance, see how large the likelihood is, or how small the likelihood, I mean, essentially it should be very small, right? How small the likelihood is, but that one is not needed if you want to simply just sample. If you want to do sampling, essentially you only need to just generate one random noise and then pass it through the generator, the trained generator, and gonna be hopefully the thing you want. Questions? No question? Okay. Now, few notes here. So as I told you, when you are updating the discriminator, you typically do multiple iterations before you update generator once. This is important because we have like an outer loop and inner loop, and really when we are updating this outer loop, we really want this inner loop to have a bit converged, right? And if you just do one iteration, it's not very expected that it's already converged, right? So you need multiple iterations. Typical choices are something between 5 and 10, right? If you put anything like that, it's going to be okay if you're just thinking of the basic data sets. And one other thing that you might get to see when you are implementing is this particular problem. So when you are, let's say you are computing the gradient of your likelihood with respect to the generator, okay? And then this likelihood, the term is essentially log of the discriminator at the data point, log of 1 minus discriminator of the model sample, right? Now, if I want to compute the gradient of this guy with respect to W, what's going to happen to the first term? It's going to be 0 because the generator is not showing up there, right? So the only thing that remains is essentially the second term, right? But this second term has a bit of numerical issue. What is the numerical issue? Say you have just started, right? When you have just started, your generated sample is not very good, right? This means that the discriminator is going to tell you that the probability of this one being real is very small, right? When it's very small, then you're going to have log of 1 minus something tiny, which is pretty much 0, right? Correct? So you are going to start with the small values. You see my point? And in that small values, your gradient is also going to be small, right? And once you get those gradients, you are just having a hard time to update. Now you keep on going and update. Say you just do your update and you just come up with some numerical trick to get rid of that issue. Then when you get your generator generating very good samples, then this probability is going to be pretty much 1, right? And then this log term is going to go to infinite, right? So you're going to see this vanishing, exploding gradient at some point. And typically you are going to get stuck with the vanishing gradient in the first place, meaning that numerically when you do this, you don't see like favorable result. One trick that people do is they, instead of computing the gradient of this guy, they compute the gradient of the minus log of d phi g, okay? So instead of log of 1 minus d, they are computing minus log of d. And the reason is that they would say it's going to be more, like in a more sensible kind of, in a more sensible, say, range, or more useful range, and then it's also pointing out towards pretty much the same direction. Because of that, sometimes people replace it with this term. So if you see some implementation and people say that this is the generator loss, this is eventually nothing but what we said. Okay? This is exactly the same thing. Just for sake of numerical stability, they're going to drop that 1 here and take that minus out of logarithm, which mathematically is not correct, but numerically it's going to converge you toward the same direction you want, faster, right? With less trouble. Everybody's clear? Okay, so these are just a few notes regarding the implementation. If you want to do sampling, as I said, you don't have any trouble. So you're essentially going to just sample latent space. And then once you sample the latent space, you're going to just pass it through the generator. Then you're going to get your sample. Okay? So this guy was essentially one of the first guys who started to just give us realistic images, right? And this is why it was like a kind of breakthrough in the generative models. And as you can see, the key point here was that we were not really obsessed with the data distribution, right?